And thank you for inviting me to giving me an opportunity to talk to such a anniversary conference. And I also want to say thank you to several wonderful results by Karen. So I actually I was helped by her results many times. Especially my favorite is your paper with Brickroom data about discreteness and rationality of jumping numbers, which motivates me to study ACCU for a PSS. So thank you very much, and congratulations for your this anniversary.
Thank you.
Okay, so I start on my talk. And I will do so. Can I do my talk until 12:10? Is it what?
Yeah, or even 15. Or even 12, 15, 15.
15.
Maybe 16. Not 17. No.
I'm sorry, you may be hungry, but okay, so I start. Okay, so this work is joint work with Tatsuro Kawakami about extending theorem in positive characteristic. So I will explain its extension theorem. So let me start from the setting. Let us assume that X is a normal variety over separation closed field, and U be a regular locus. Then, okay, so we can define omega x bracket I, which is a switch forward of omega u over k, which I, where iota is of course inclusion. So this is a reflexive halo of I's ratio for tangent bundle. So this is the main theme of today's talk. So let us assume. So even if we are in positive characteristics, so today we assume that there exists a log resolution. But this is not so essential assumption. So this is just for simplicity. So just for simplicity, we assume that there exists a log resolution of X, and which is isomorphic on U, smooth locus. So we start from this setting, and let E be an exceptional locus, which is SMC because this is log resolution. We define the log extension theorem and regular extension theorem. So we say that X satisfies regular extension theorem. For items if the switch forward of omega y is coincides with the bracket of item over x. So this, if this satisfies, then we say that x satisfies the regular extension theorem for items, and I write this by RET I. Okay, so this is the definition of regular extension theorem. And finally, we assume that X is, so this is extension theorem. So to explain this, so I can give an equivalent condition when X is affine. If X is affine, then this is equivalent to saying that the global section of I forms over Y to a section of mu is surjective, because this right hand side is just the sheaf associated with this motion, and the left hand side is the okay, let's see how associated this. So this is the actually equivalent. And this is just the restriction map because U is of course open subset of Y. So this is just a restriction map, and this is surjective with equivalent to this regular extension theorem. In other words, so this is also equivalent to saying that for any iPhone U, so this is the element of here, extends to some iPhone data on Y. Because surjectivity implies so there exists some element which maps to alpha. So this is the equivalent condition. And okay. So this is the reason why this is the extension theorem. Okay, so the motivation is very clear. So this notion is very important. Okay. So this is the definition of regular extension theorem. And I also define logarithmic extension theorem. Logarithmic extension theorem for iPhones. Which I may like LEPI. It's equivalent to saying that expression of the log iPhone, so iPhone with pole along E is equivalent to omega xi. This is the a bit weaker condition than regular extension theorem, but we say that logarithmic extension theorem in this case. Okay, so this is the definition. And this is very interesting notion because there is this deep connection is singularities in MMP. So we explain this one. This thing. So for simplicity, so here, so we need to assume that the characteristic is 0. And for simplicity, we assume that X is poema coherent. In this case, so there is a notion of singularities in MMP, which is called rational singularities. X has only rational singularity. This is almost definition because we assume X is poema coherent. So since X is poema coherent, this is almost definition, but say rational singularity is defined by saying that X star of omega Y coincides with omega X. But this is actually so omega Y is the weight of dimension. So D is the dimension. This is like the definition of omega Y. And omega X is of course this bracket of omega X. So this is by definition equivalent to regular extension theorem for D forms. Okay, so regular extension theorem is something like the generalization of rational singularity. How about logarithmic extension theorem? So there is another implication. So, sorry. For instance, there is a notion of Dubois singularity, which I don't define today. But if X is poema coherent, there is a nice equivalent condition for Dubois singularities, which is done by Kawakami. So in poema coherent case, Dubois singularity is equivalent to saying that X star of omega Y capital E is omega X. But this is actually, so I'm sorry, I don't define the log version of potential demand, but this is actually equal to this notion. So this is equivalent to extension theorem for deforms. So logic extension theorem is somehow a generalization of Riemann singularities. But surprisingly, this is not a generalization because there is a good result which is proved recently. So by definition, regular extension theorem for D form is equivalent to rational singularities, but it implies regular extension theorem for any form. This is surprising result, which is proved by Kenta Sato. On the other hand, if we assume that the singularity is before, then similar thing holds for all R. So this is proved by yeah. Okay, so this is the overview of regular extension theorem and logic extension theorem in characteristic zero.
In positive characteristic, do you have any kind of result which says that regular extension theorem for I forms implies regular extension theorem for I minus 1 form?
No. What do you mean? I form for regular extension theorem for I minus 1.
Yeah, in positive characteristics.
I think I don't know. I don't know. And I think so. Even if this is true, so the proof may be very different. So, I don't know. Okay, so next. So today we consider the positive characteristic case powered in positive characteristic. So I have no time to define the definition of singularities, but people may know. And so I just write a diagram and, instead of definition of singularities. So there is many notions in positive characteristic. So one is irregular or strongly irregular, one is pure, one is rational. There is also equivalent, which is a counterpart of singularities in MMP, LP, LC, and rational singularities, and Riemann singularities. This is a diagram written by Kevin Stock. Okay. So naturally, so for example, so in characteristic zero, rational singularities implies regular extension theorem. So and this is equivalent to logic extension theorem. So natural question is that if rational implies regular extension theorem. Okay, but surprisingly, this is not the okay. So answer is no. Which is given by graph. So there exists. So let us consider characteristic P condition and the P Veronese ring of polynomial ring. Then this is irregular because this is the direct summand of the polynomial ring. But this does not satisfy regular extension theorem for one form. Not. sorry, equilibrium button not satisfies the regular extension theorem. So the situation is very subtle in characteristics. But how about regular extension theorem? So this is somehow more hopeful. So because there are several positive affirmative answer, partial affirmative answer for this situation. For example, first one given by graph, it says that x is two-dimensional regular variety over algebraic closed field. Then it satisfies logarithmic extension theorem for one form. Okay. So of course, equilibrium. So this example says that equilibrium but so equilibrium but not regular extension theorem. Equirational is weaker than this stronger than this notion. So this is also no. But equilibrium implies that the logarithmic extension theorem is okay in dimension 2. Okay, so today's main theorem proves that this is okay in 4 dimensions. So in any dimension, equilibrium singularity satisfies regular extension theorem for one form.
You mean the log?
Sorry, locus. Thank you. Okay, so this is today's main theorem.
I still want to clarify a question. You're talking about strong irregular, right? Or are you actually working with tight closure?
Sorry?
You're working with strong irregularity.
Strong equilibrium.
I'm just clarifying.
Sorry.
You don't have to write it.
Yeah. Sorry.
You don't have to. I would like it to disappear. But I just want to clarify. Mel disappears. You don't have to. Yeah, you're just old.
Okay, so I will explain the main idea of
Sorry,
yes.
can I ask so this theorem you are also assuming there is a resolution of singleton under prior to
No, we don't have to assume resolution.
Okay.
So the in this talk, so I assume the existence of resolution for defining logic extension theorem, but I don't have to I assume that the existence. So actually, so this is defined like this. So for any birational is normal y, something like some similar condition for. So this is the definition. So we don't have to assume the existence of the resolution. Okay. I will explain a key point of the proof. So one of the key points is like this. So this is not trivial. So this is the name about this is so like that. Okay, so this is actually not trivial. So it says that if x is certainly pure. Yes, pure. And sorry, and satisfy the tail condition S3 and dimension 2. Then so the key point says that so if x is satisfies this condition, then to verify logic extension theorem, then we need only check logic extension theorem in fundamental 2. So this is the key point. So the proof of this theorem is not so easy. So we use parity operator and some binding of local cosmology. And so on. By the way, so I don't focus this theorem. So today we focus on the so after this theorem. So by using this theorem, so we can localize x at codimension 2 point. So the essential point is that so let R be a localization of x at some codimension 2 point, which is like this, so normal essential of finite type over algebraically closed field, and just in dimension 2. And if R is strongly irregular, then it implies R satisfies logic extension theorem for one form. So by using this theorem and key theorem, we can solve the theorem A. We focus on the proof of theorem B.
And how does that differ from fact one?
Yes, thank you for the nice question. So I explained the relation with fact one. So if the residual field of R is equal to the base field, then theorem B is nothing but fact one. So it's okay. By graph, fact one by graph. But so the theorem B is just only the difference is this is not equal in theorem B. So it seems a bit not so serious, but actually so the proof is not so easy. So I explain why so this assumption is very important. So to explain, so we give a idea of fact one. So one of the key points is the classification of dual graph over strongly irregular singularities in dimension 2. Using this, so we can do case by case argument. And so for simplicity, we only explain the most of trivial case. So today we focus on the exceptional divisor is useful. So the dual graph is just a point. So I explain only this case. So in this case, so since we know this is a strongly irregular volatility, the genus of E is of course 0. So it's P1K. And actually, why is why is the minimal why is the minimal resolution? Why is minimal resolution? The pair of Y is of course is simple normal crossing, but if simple normal crossing, then there is a good exact sequence. Which is called residue exact sequence and restriction exact sequence. I will write here. Okay, so what is the this is taking residue. Sorry. This is taking residue. Yeah. Which is exact. And the other is the restriction exact sequence. Is like this. Omega y1 to omega 1 to 0. This is the restriction map. So we have such a exact sequence. And by using, so this is just invertible sequence P1. They are invertible sequence P1. So we can know everything of them. So by using this, so actually we can show that the global section of omega log E is equal to H0 over omega 1 E by using this part, tensor E. And this is also equal to H0 over omega Y log E tensor E by using the first exact sequence tensor E. So this shows that H0 global section of omega Y log E is equivalent to omega Y, the global section of omega 1 log E tensor E. So repeating, so we can say that so this is equal to omega 1 log E tensor E for any positive integer n. But if n is sufficiently large, this becomes larger and larger and numerically equivalent to omega x1. So this is so this is just a logarithmic extension theorem. So this is the sketch of the proof. Okay, so what is the problem if the residue field is not equal to the base field? It is so there are several problems, but I focus only one problem. So one of the problem and this condition, our condition. So we say that so in the above idea, so we use that the curve of genus 0 is P1, but this is not true. If kappa is not algebraically closed. This is the problem. So this is not equal, but moreover, so it may not be smooth. And moreover, it may not be geometrically reduced. This is the problem, because if it is not smooth, then we can use that sequence, because that sequence follows from the SNC condition.
Sorry, your E is the reduced exceptional device?
Yes, sorry. So yes, actually, reduce will, just here, so we only assume is a projective integral. Okay, so this is the problem. And actually, so such a situation often occurs in our situation, because, so for example, let us consider R, which is okay. So this is not only in positive characteristic argument, but also in characteristic zero problem. So for example, let R be a R algebra, which is defined like this: x squared plus y squared plus z cubed. That is the exceptional divisor of minimal resolution. So the minimal resolution of this singularity is actually, so by growing up one point. Growing up origin, then this is why the minimal why is regular and this is minimal resolution. But the exceptional locus is a cross of R x y z over x squared plus y squared. So it is a integral over R, but singular at the origin 0, 0, 1. This is one of the problem. So it may not be smooth even if, so this is of course is 0, but this is not smooth. But this case is not so serious, because not so serious. Because actually, so these singularities can be resolved by data recovery. So this is the SMC, because so this is this is decomposed into two lines. So up to the recovery, so this case is not so serious. But there is a serious case in positive characteristic, especially in characteristic 2. So let's take the characteristic field, imperfect field, and R is hyper surface defined by this equation x squared plus sy squared plus tz squared, where s and t are contained in the position field. So what is this singularity? This singularity is also resolved by single blow up. So then this is regular. So minimal resolution. And the exceptional curve is approach of this, which is not smooth over kappa. Sorry, kappa is in this case. Sorry. In this case, the residual field is of course base field, but in this case, we don't assume this is algebraically closed. So in this case, residual field is not algebraically closed. So this is a problem, and which shows that this is not smooth over kappa. And more worse, so this is not geometrically reduced over kappa, because the base change of this curve to algebraically closed field is so this becomes this. Yeah, so this is not revealed. Yeah, so this is the bold line. So in this case, the singularity of R is KLP. So this is KLP. But the exceptional curve is not geometrically used. So this is very bad singularity, which is essentially difficult to overcome. But so we can prove that we don't have to consider this case. Our theory is that. So this is just just a KDT case, but in theorem C, we say that if Rm is two-dimensional and strongly regular singularity, then if we take minimal resolution, then every exceptional curve is geometrically reduced. Okay. So this says that, so if we assume strongly irregular, then such a bad thing does not occur. And actually, so in this example, so this R is not irregular. So this is our situation.
Can I ask a question? Do you know anything about that in higher dimension?
I'm sorry.
Do you know anything about that theorem C in higher dimension?
For I mentioned I don't know, but I think we cannot form something like that. I have no evidence. Maybe so. I think that there may be counterexample in the okay. Okay, so and actually, so this theorem C is one of the key points of your group theorems B. Because once we know exceptional curve is geometrically reduced with genus 0, then we can treat these curves. So we can prove theorem B, and theorem B implies theorem A by using this theorem. In the last 15 minutes, I also talk about the classification result of equilibrium surface and singularities. So this theorem is one of the key points to prove the to find the classification of strongly figures of singularities. So before stating, I give a notation. So from now on, R is always a finite normal local ink of dimension 2. And F is a minimal resolution. And we add exceptional locus like this. Yeah, the irreducible decomposition of exceptional locus is like this. So in this case, we can define the dual graph as following. So this graph has a vertex. So n vertex, one of them corresponds to each EI. And the number of edges between EI and the EZ is defined by the intersection number of EI and EZ. And finally, each vertex will give three weights. So one is the genus. And the second is the self-intersection number. So this is a classical dual graph. But in our case, we need another way, which is like Ri, which is defined like this. So the global section of EI is some field extension of kappa, but the extension degree is Ri, which is the final result of EI. So this is the dual graph in our setting. So for example, K is the arbitrary field, and A is the element of K, which satisfies this condition. So we assume this condition. And let us consider the hypersurface singularities defined by z squared plus x cubed minus a times y cubed plus y seventh. Then the minimal resolution is like this. So there are two exceptional curves. One is P1A, where L is the extension of K, adding this element. And the other side is just a P1K. And the intersection is the scheme theoretic intersection that like step L. So this is the situation of this example. So the dual graph of this example is like this. So we like two vertex, one is E1, and another is E2. And GH is a intersection number of E1 and E2, which is a length of this scheme theoretic intersection number over base field or residue field of R. So now we have this is this 3. So we write 3 edges here. And we have a weight is like this. So here, so the self-intersection number is -2, and R1 is 1 because H0 is 1 is actually base field. And the genus is 0 because this is P1. How about A1? So genus is 0, but self-intersection number is -6, and R is 3 because H0 or E2 is 8, so it is a 3 degree. It has 3 degree. This is example. Okay. So in terms of this dual graph, we obtain the classification result, which is proved by us, but Nobuohara proved in 98 in the case of algebraically closed case. So we speak instead of Hara's classification, which says that R is strongly irregular if and only if. Sorry, so R is actually this setting. But in this case, R is strongly irregular if the following two conditions satisfied. The first condition is that every exceptional term in minimal resolution is geometrically reduced. And second, one is the following, which is very similar to Hara's classification. So one is gamma is folding of. I will explain what is folding, but gamma is a folding of a chain. The second case is that so the characteristic is larger than 3, sorry, characteristic. Characteristic is not true. And the dual graph is a folding of three over type 3 or some. So this is the second case. In the third case, it is not 2 or 3, and gamma is a folding of 3 of 2, 3, 3, or 2, 3, 5, 2, 3, 4. And final case, so as you can imagine, so gamma is a folding of 3 of 2, 3, 5. Okay, so this is the classification from irregular singularity in non-perfect setting. What is the following? So for example, so in this in this case, so we explain by using example. But in this case, this is the folding of the graph like this: minus 2, 1, 0, minus 2, 1, 0, and minus 2, 1, 0, minus 2, 1, 0. Okay, so folding means some part of so we fold some of them. So in this example, so we fold these three vertex to here, and the weight becomes summation for these and this. GRC is a bit similar. You don't have to consider. Okay, so this is an example of folding. So. And okay. So for example, in this example, so this graph is a 3 of 2. So this gamma is a folding of 3 of 2. So as in this case, so this example is here in this case. So by using this classification, this R is strongly regular if is not 2 or 3. Okay, so here, so we only assume P is not 2, but so okay, so if P is 2, then this is not strongly regular by this condition. But even in the case of P is 3, this is also not strongly regular because this is not geometrically reduced over the basis. So this does not satisfy the first condition. So this is not strongly regular. But in this case, they are geometrically reduced and the graph is also okay. So this is strongly regular. Okay. And finally, so by using this classification, I give a corollary. This is also surprising. So let's assume Rn and R contains some field of positive characteristic, and this is normal, defined, and dimension is 2. So we further assume that the residual field is separable over small k, and we also assume that R is geometrically normal over k. This is essentially equivalent to R is smooth or R is smooth over k outside of 0 maximum here. But in this case, if R is strongly regular, then it is geometrically strongly regular over the base. Here, geometrically implies so roughly speaking, the base tends to algebraically closed field is strongly regular. Okay, so we can show it by corollary C, by corollary by theorem C, because actually the second condition is not preserved under, seems preserved under very but okay. So, anyway, so I can prove corollary easy, but I skip because of time. Okay, thank you very much.
Okay, so my question is actually about the first part of your talk.
Yes.
So the question is, do you have any class of varieties where the full logarithmic extension theorem holds? For example, if you have more stronger assumption like globally irregularity or X or something like that, when you have all the vanishings.
Sorry. So your question is about the regular extension theorem?
Logarithmic extension theorem. Logarithmic extension holds for all forms. Not only just one form, all forms.
Yes. So, actually, so we only prove that logarithmic extension theorem for one form.
Yeah, but you are assuming it's strongly irregular, right?
Yes.
So if you assume more strong, like globally irregular, when you have all vanishings.
So this is just a local thing, so global is not. This is local question, so global is not. But
well,
I hope so. I think so. This may be happen. So I only prove this, but maybe this clear. I don't know.
I have a simple question.
Yes.
Is there a characterization in characteristic view of the one singularity?
Dubois is so actually the definition of Dubois is I'm not familiar with Dubois, but in my understanding, so to define Dubois, we need to assume characteristic is zero. So,
But Carl has the F injective implies Dubois.
yes. So F injective is the counterpart of Dubois. So this is the best thing I think in question. That is the one question.
Any questions? If not, let's thank Kenta again.